BSc Chemistry, IR Spectra, presented by Dr. Giridhar M., Assistant Professor of Chemistry, Department of Collegiate Education. IR Spectra contents. So in this session, we will be studying Introduction to IR Spectroscopy, the range of infrared radiation, vibrational spectra of diatomic molecules, force constant, expression for vibrational energy, zero-point energy, vibration modes of polyatomic linear molecules, vibrational modes of polyatomic non-linear molecules, application of IR spectroscopy. So let us start with Introduction to IR spectroscopy. So IR spectroscopy is one of the most powerful analytical technique which offers possibility of chemical identification of organic and inorganic structure. So from using IR spectroscopy, we can find the type of functional group which is present in the organic molecule, and in combination with other techniques such as NMR mass spectroscopy, we can use this technique to find the complete structure of molecule. The technique is based on simple fact that chemical substance shows selective absorption in the infrared region. After absorption of infrared radiation, the molecule vibrates at many rates of vibration, giving rise to close-packed absorption bands called IR absorption spectrum, which may extend over a wide wavelength range. So once we pass the IR radiation on molecule, the molecule shows selective absorption, and this selective absorption means here the absorption of radiation depends upon type of bonds which are present in the molecule, and therefore it gives an opportunity for structural identification of molecule. Various bands will be present in IR spectrum which corresponds to the characteristic functional group, the bond present in chemical substance. Thus, an IR spectrum of chemical substance is fingerprint for its identification. The molecule absorbs radiation only when natural frequency of vibration of bond in molecule is same as frequency of incident radiation. So that means natural frequency of vibration of bond should match that of the frequency of radiation which we are incidenting on the sample. Say for example, if our molecule contains OH bond, OH frequency of vibration is around 3300 per centimeter, and when we are putting IR radiation on that molecule, it will absorb only radiation corresponding to its vibrational frequency, that is 3300 per centimeter. A molecule can only absorb radiation when its absorption changes in dipole moment. So this is one important condition for molecule to exhibit IR spectroscopy. That means the molecule must undergo change in dipole moment, okay, during absorption of radiation. So here homonuclear diatomic molecules are IR inactive because there is no change in dipole moment in these molecules. The dipole moment of oxygen, nitrogen and hydrogen are zero, and hence they are IR inactive. The range of infrared radiation. The infrared radiation refers broadly to that region of electromagnetic spectrum which lies between visible and microwave region. So that means in electromagnetic spectrum, the region of infrared occurs between microwave and visible region. And further, this infrared region can be divided into 4 sections. That first one we call it as photographic region. So this ranges from visible to 1.2 micrometer frequency. Very near infrared region, this is also known as overtone region and ranges from 1.2 to 2.5 micrometer. Near infrared region This is also known as vibrational region and ranges from 2.5 to 25 micrometer. So it is in this region most of the functional groups vibrate. Hence it is also called as vibrational region. Far infrared region, this is known as rotation region and ranges from 25 to 400 micrometer. When analytical chemist speaks of infrared spectroscopy, he usually means the range from 2.5 to 25 micrometer or 4000 to 400 per centimeter in terms of wave number. Okay, so this is in terms of wave number, 400 to 4000 per centimeter. So this range gives the important information about the vibration of molecule and hence about the structure of molecule. The IR spectrum is a graph of transmittance or absorbance versus wave number. So in the IR spectrum, if you see on the x-axis we have wave number from 400 to 4000 per centimeter, and on y-axis absorbance will be there. Okay, absorbance 0 to 100. So vibrational spectra of diatomic molecule. Force constant. Force constant are the proportionality coefficients between the displacement of atoms from their equilibrium positions and force they induce on other atoms. So here we know that bonds are not static. Okay, the bonds are not static. They are like spring. So that means these bonds keep vibrating at their equilibrium position. They continuously keep vibrating. Okay, along its internuclear axis, and that vibration is given in terms of frequency of vibration, which is nu, which is frequency of vibration. K is force constant, mu is reduced mass, and here frequency of vibration is directly proportional to square root of force constant, and it is inversely proportional to square root of reduced mass. So here force constant is nothing but the measure of strength of the bond. So if force constant is very much higher, the bond strength will be higher, and hence we require higher frequency of radiation, or the vibrational frequency of the bond will be higher. If the force constant will be lower, then the vibrational frequency of the bond will also be lower. So m is the reduced mass. Reduced mass is given by m1 into m2 divided by m1 and m2, where m1 and m2 are the masses of two bonded atoms. So therefore, in simple, we can say that force constant is the measure of strength of bond. Expression for vibrational energy. So here vibrational energy for diatomic molecule is obtained by solving the Schrödinger wave equation. So here on solving the Schrödinger wave equation, we get vibrational energy, which is E is equal to V plus 1 by 2 hc omega, where h is Planck's quantum number and V is vibrational quantum number. It can have values from 0, 1, 2, 3, and omega is vibrational frequency, and c is the speed of light. So this is the energy of vibrating diatomic molecule. So by substituting the values in vibrational energy, we get different values. So E nu is equal to 1 by 2 hc omega when V is equal to 0. When V is equal to 1, it is 3 by 2 hc omega. When V is equal to 2, it is 5 by 2 hc omega. So here we are substituting the value 0. When we substitute value 0, E0 is equal to 1 by 2 hc omega. When we substitute value 1, so it is 3 by 2 hc omega. So and by using Hooke's law, okay, when we plot this energy in Hooke's law, 1 by 2 kx square, which is the potential energy of that vibrating diatomic molecule, we get different energy levels like this. This is E0, E1, E2, E3, E4. So like this. These are the vibrational, different vibrational energy at different values of n. 0 point energy. 0 point energy is the vibrational energy that molecule retain even at the absolute zero temperature. So at absolute zero, it is not, the energy of the molecule is not zero. Instead, it is 1 by 2 Hc omega. So even at absolute zero, the molecule retains some amount of vibrational energy. Okay, so E energy is given by nu plus 1 by 2 Hc omega. When we put the value of nu 0, it will be 1 by 2 Hc omega, and this is called as 0 point energy. So even at absolute zero temperature, the molecule retains some amount of minimum energy, okay, and that is called as 0 point energy of the molecule. Transition. So when transition takes place, the electron will jump from V to V plus 1. So then it is given by delta E. The difference in energy is given by V plus 1 by 2 Hc omega minus V plus 1 by 2 Hc omega. So and here this cancels out. Okay, V 1 by 2 cancels out 1. So this will be only Hc omega. Okay, and delta E by Hc is equal to delta nu omega. So therefore, transition taking place from nu is equal to 0 to nu is equal to 1, the frequency obtained is called as fundamental frequency. Okay, this is called as fundamental frequency. So the only line obtained in the vibrational spectrum whose wave number is equal to equilibrium vibrational frequency of diatomic molecule. So this is called as fundamental frequency of vibration. Fundamental frequency of vibration. That is, so when electron jumps from this energy level to this energy level, it is called fundamental vibrational frequency. When electron jumps from here to here, it is called as fundamental vibrational frequency. If the electron jumps from n is equal to 0 to n is equal to 2, it will be twice the fundamental frequency, and it is called as overtone. So selection rule and transitions. So when molecule absorbs IR radiation, transition occurs from ground vibrational state to excited vibrational state. For molecule to be IR active, there must be change in the dipole moment as a result of vibration that occurs when IR radiation is absorbed. And selection rules are given as delta nu is equal to 0 plus or minus 1 plus or minus 2. Okay, this is for vibration mode. And rotation, delta J is equal to 0 plus or minus 1. So that means, so here we can clearly see that two things. One is molecule must have dipole moment, or it must undergo change in dipole moment when it absorbs radiation. And second thing, the second selection rule is transition. When transition takes place, that delta nu should be 0 or plus or minus 1 or plus or minus 2, and delta J should be 0 plus or minus. Types of stretching and bending vibrations. Absorption of IR radiation causes bonds to stretch and bend. Stretching corresponds to increase and decrease in bond length within a molecule, and bending corresponds to increase and decrease in bond angle in the molecule. Stretching is of two types. So one is symmetric stretching, so as shown in the figure, symmetric stretching and asymmetric stretching. So this is asymmetric stretching. And bending are also of two types. One is in-plane bending. In-plane bending can be scissoring and rocking. So these are in plane bending and out of plane bending. Out of plane bending is wagging and twisting. So these are the types of stretching and bending which takes place in the molecule on absorption of radiation. One. So these are the selection rules. So let us see some example. So for linear molecules, the number of degrees of freedom, total number of degrees of freedom is given by 3n minus 5. So where 3n is total degrees of freedom, that means it contains vibrational degrees of freedom, rotational degrees of freedom, translational degrees of freedom. So here linear molecule, so if we place this linear molecule along z-axis, we see that the molecule can rotate like this, okay, along x-axis and also along y-axis, but on z-axis it is rotating along its internuclear axis, and therefore only 2 rotational degrees of freedom is possible. In case of translational motion, the molecule translational motion is nothing but kinetic energy. So the molecule can move from one place to another place. It is not like rotation. Translational motion is the molecule moves from one region to another region. So the molecule, if this is the point of the molecule, it can move in x-axis, it can also move in y-axis, it can also move in z-axis. Therefore 3 translational degrees of freedom will be there. So therefore vibrational degrees of freedom is calculated as total degrees of freedom minus rotational and translational degrees of freedom. So 3n minus 3 plus 2, 3n minus 5. So where n is the number of atoms present in the molecule. Say for example, if I take HCl, n will be 2 atoms will be present. CO2, carbon dioxide, 3. N value of n will be 3 because in this 3 atoms will be present. So let us take one example, that is carbon dioxide. Carbon dioxide is linear molecule. It's a polyatomic linear molecule. So for this 3n minus 5, that is 3 into 3, 9 minus 5, 4 normal modes of vibration will be present. So as I already told, n is the number of atoms. 4 normal modes of vibration, and these are shown in the image. A is called symmetric stretching, B is asymmetric stretching, C is symmetric bending, D is asymmetric bending, and A, it is symmetric stretching. Symmetric stretching does not produce any change in the dipole moment. So the dipole moment of this stretching is 0. The dipole moment of this molecule is 0. Even after absorption of radiation, it does not produce any change in the dipole moment, and therefore in the IR spectrum we see 3 peaks, one for okay, asymmetric stretching, another for asymmetric bending, and another one for symmetric bending, and another for asymmetric bending. So for nonlinear molecules, so it has 3 rotational degrees of freedom and 3 translational degrees of freedom. Therefore vibrational degrees of freedom will be 3n minus 3 plus 3, that is 3n minus 6. So this is for water molecule. Water molecule has bent structure. So this is non-linear molecule. So for non-linear molecule, as I already told, 3n minus 6. 3 into 3 minus 6 is equal to 3 fundamental modes of vibration. We observe 3 fundamental modes of vibration. So here one is symmetric stretching, this is asymmetric stretching, and this one is bending. So 2 types of vibrational modes will be present. One will be symmetric stretching and bending. In stretching, symmetric stretching and asymmetric stretching will be there. In bending, we have different types of bending like scissoring, rocking, so etc. Therefore, there are three vibrational modes of water. So one appears at 3652 per centimeter for symmetric stretching, another at 3756 per centimeter for antisymmetric stretching, and 1595 per centimeter for symmetric bending. So lastly, application of IR spectroscopy. One, it is used in the detection of functional groups. To find the moment of inertia and bond length can be calculated. 3, for calculation of force constant it can be used, and force constant gives the strength of the bond. It can also be used in qualitative analysis, that is to compare the spectra of unknown compounds with the standard and identification of new compound. For quantitative analysis, impurity reduces the sharpness of the peak. So from the study of this peak, percentage purity can be calculated. So these are the some of the applications of IR spectroscopy. One is detection of functional group, detection of moment of inertia and bond length, calculation of force constant for qualitative and quantitative analysis. So these are the references. So thank you.